integral to our daily lives. Iron ore from the Hercules mines in the Coahuila Desert is transported as a slurry through a 14-inch diameter, 180-mile-long pipeline to the pelletizing plant. Upon arrival, the slurry is filtered to recover water, and the dry ore is then sent to pelletizer discs. Here, it is mixed with binding agents to form small balls called pellets. These pellets are heat-hardened at 1,300 degrees Celsius before being sent to blast furnaces. Coal processing. Metallurgical coal, transported by rail from the Carboniferous region of Coahuila, is treated in vertical ovens lined with refractory brick. Through an 18-hour baking process, the coal is transformed into coke, the basic fuel for blast furnaces that produce pig iron. This coking process also produces valuable byproducts like coke oven gas, which is used in later stages of steelmaking. Sintering. Sintering is another critical process that prepares raw materials for the blast furnace. A porous mass composed of iron ore flakes and powder, blended with lime, coke fines, and dolomite, is hardened in a continuous chain oven. This mass, known as sinter, along with pellets and coke, serves as a primary input for the blast furnaces. Blast furnace operation. The blast furnaces at Acero are large cylindrical structures, over 160 feet high, lined with refractory brick. They are designed to convert the iron oxides in the pellets and sinter into pig iron. Charging the furnace. Raw materials such as pellets, sinter, limestone, dolomite, and coke are stored in hoppers and deposited into the blast furnaces through a charging system located at the top. Smelting. Hot air, introduced under pressure at the furnace's bottom, blasts the coke and smelts the iron ore at temperatures up to 1,650 degrees Celsius. The molten metal collects in a graphite hearth at the furnace's base and is then drained through tap holes into 200 metric ton capacity torpedo cars. Desulfurization. The molten pig iron undergoes desulfurization, where reagents like calcium carbide and magnesium are added to reduce sulfur content. The resulting slag is cooled with water, stored, or sold as a byproduct. Steelmaking processes. Acero employs two primary methods for converting pig iron into steel: the basic oxygen furnace, BOF, and the electric arc furnace, EAF. Basic oxygen furnace, BOF. Scrap metal is first loaded into pear-shaped refractory-lined converters with capacities of up to 150 metric tons. Molten pig iron is then added, and oxygen, argon, and nitrogen are injected into the mix under pressure through lances. This process refines the metal into liquid steel in about 45 minutes. Ferroalloys are added to adjust the steel's chemical composition as per client specifications. Electric arc furnace, EAF. The EAF process begins with a mixture of scrap metal, iron briquettes, or liquid pig iron, typically at 150 metric tons per cast. The furnace uses 3 graphite electrodes to apply 140 megawatts of electric energy, melting the load to produce steel. The liquid steel is then transferred into special ladles. Secondary treatment. Liquid steel from both the BOF and EAF processes undergoes secondary treatment to achieve specific properties. This involves secondary metallurgy, ladle metallurgy or chemical reheating, dual degassing, reducing hydrogen and carbon content for higher quality applications. Once the steel undergoes secondary treatment for refining, it is directed to the continuous casting machines. Liquid steel is poured from a ladle into a tundish, which serves as a reservoir, maintaining a steady flow of steel to the mold below. The steel enters a water-cooled copper mold where it begins to solidify. The outer shell forms quickly due to rapid cooling, while the inner core remains molten. As the partially solidified steel exits the mold, it is supported by a series of rollers. The strand is carefully withdrawn and straightened while being continuously cooled with water sprays. Complete solidification occurs as the strand moves through the secondary cooling zone. Once fully solidified, the continuous slab is cut to the desired length using oxy-fuel torches. This process results in slabs of uniform thickness and quality, ready for further processing in the hot rolling mill. Rolling and finishing. Hot rolling. The hot rolling department, considered the backbone of the company operations, processes the slabs in two main lines: plate lines. Reheat slabs to 1,330 degrees Celsius and use reversing mills to generate plates in the desired thickness and width. Hot strip line. Slabs are reduced in the universal reversing mill to a thickness of 2 inches and further reduced to 1 inch on the finishing mill. The final thickness is achieved on a 6-stand finishing mill train. The hot-rolled coil is either shipped directly to customers or sent to the cold rolling departments for further processing. Cold rolling. The cold rolling process reduces the sheet's thickness and enhances its physical properties. After pickling to remove oxides, the strip is cooled to room temperature and passed through various mills. Annealing in continuous heating ovens softens the material, and tempering mills improve surface quality and hardness. The mill also operates skin pass and tension leveling lines for hot-rolled and cold-rolled coils, ensuring uniform thickness and surface quality. Specialty products. The mill produces specialty products like tin plate and tin-free steel for metal container manufacturing. These products involve cold-rolled coils subjected to electrolyte baths with tin and chrome, respectively. Structural shapes. This mill is a primary domestic manufacturer of structural steel for the construction industry. This involves cutting slabs into blooms, reheating them, and rolling them into structural shapes like W shapes, C shapes, and angled L shapes. The fabrication of H-beams begins with cutting steel plates to the required dimensions. High-precision cutting methods, such as CNC plasma cutting, laser cutting, or oxy-fuel cutting, are employed to ensure accurate dimensions and clean edges. The cutting process is crucial as it determines the final dimensions and quality of the H-beams. The plates are typically made from high-strength structural steel, chosen for its excellent mechanical properties and durability. Assembling plates into an H-shape. Once the steel plates are cut, they are assembled into the characteristic H-shape. This assembly process involves positioning 2 flange plates and 1 web plate. The web plate is placed vertically between the 2 horizontal flange plates. Alignment is critical at this stage to ensure the structural integrity and load-bearing capacity of the final H-beam. Fixtures and clamps are used to hold the plates in position while they are being assembled. Automated assembly lines can streamline this process, ensuring precision and efficiency. H-beam welding. After the plates are correctly positioned and clamped, the welding process begins. The most common welding methods for H-beam fabrication are submerged arc welding, SAW, and gas metal arc welding, GMAW. These methods are chosen for their ability to produce strong, consistent welds. Tack welding. Initially, tack welds are applied at strategic points along the plates to hold them together. This prevents any movement during the main welding process. Main welding. The main welding process involves running continuous welds along the joints where the web plate meets the flange plates. Automated welding machines equipped with multiple welding heads are often used to perform this task efficiently. These machines ensure consistent weld quality and speed up the fabrication process. Post-welding. After welding, the H-beams undergo inspection to check for any defects or inconsistencies in the welds. Non-destructive testing methods, such as ultrasonic testing, may be employed to ensure the welds meet the required standards. The manufacturing process for steel structures in shipyards involves several key stages to ensure high quality and on-time delivery. Initially, The concept and design phases are integrated closely with production to optimize material use, weight, and required operational standards. This two-way process facilitates finding optimal solutions for each project. Once the design is finalized, production takes place in modern, custom-built facilities designed for controlled indoor conditions, essential for tasks like blasting and painting. Pre-treated materials are used to enhance durability and quality. Professional staff, equipped with special skills and regularly trained, oversee the manufacturing process, ensuring adherence to technical specifications and standards. Quality control is rigorous, with experienced supervisors and controllers permanently stationed at partner plants. Each production stage is documented, with control reports and measurement protocols submitted to maintain transparency and compliance with customer requirements. The final products are inspected and approved by classification societies. Logistics play a crucial role in ensuring on-time deliveries. Proven global logistics partners handle the safe transport of cargo, which is surveyed and insured before shipment.